Welcome to the CS210 video. We're going to review the memory instructions in the TSC assembler and simulator. Now, looking at the programmer's reference, there are two instructions that deal with memory, and that happens to be the load word and the store word. Now, the load word is to copy something from a register into memory, and the store word copies something from memory into a register. So let's click on it and see what it looks like. Here's the opcode. It has two registers and an address offset, which I will review shortly. But basically, if you look at the register transfer language, there's kind of a lot going on. This symbol means concatenate. So we're taking the address offset, we're concatenating it with something, we're adding that to a register, and then the data comes out of memory and goes into another register. So what exactly does that all mean? Basically, we have a base register that points somewhere to memory, or a register that has a memory address inside of it. Now, we might not want to get the data that's exactly at that memory address, so the TSC gives you the option to add an offset that will slightly offset which memory location we're going to use. And this could be helpful in arrays where the memory address is the very first location of memory, and then we can add an offset. Say we want the fifth element out, we can add 5 to the memory address and move 5 slots down in memory to get the data we want. Or if we don't want an address offset, if we do want where the memory is located, we can put 0 in this spot right here. So RS is the register that contains the memory address, and RT is the register that we want the data from memory to go into. Now, store word is almost exactly the same, except the opposite. Instead of taking the data out of memory and putting it into the register, we're taking data from a register and putting it into memory. So that's the store word operation. So let's go ahead and write a couple assembly programs to show you exactly how these instructions might work. So I created a new assembly file or a new .tsc file. And remember, you have to have the extension be .tsc. And I'm going to write a program, and the .org says I want this program to go into memory location 0000, and this will be the end of my program. So the first thing I'll do is I'll just put a number into a register, and then I want to store that number into memory at some location. So the command to do that will be the store word command. So let's go ahead and put down our registers down here in comments. So now that we have this, now again, you can write this on a piece of paper, and maybe we'll use register 0 for the number we want to store inside of a register. So what number? Just come up with a random number. I'll say 35. And this is, the purpose is data to store in memory. And next, we need a location to store it in memory. Now I could store this wherever I want, but there might be a few things that I want to avoid. I probably don't want to overwrite my program itself, so it would be really silly to store my data over my instructions that are going at memory location 0000. So maybe let's choose a different spot. Maybe we'll choose a hex value of 100 to store it. So I don't think I'm going to use more than 100 instructions for my program. So storing my data at memory location 100 will be okay. And then the purpose is memory address to store the data. Okay. And then registers 2 and 3, I don't think we'll need to use. We'll just need to get this up first. So I want to load an address into register 0 of 35. Now remember, load address may be somewhat misnamed because it can also load data or numbers into a register. So this just puts 35 into a register. Also remember, it's going to get split into 2 instructions, a load high immediate and an OR immediate instruction. Next, we'll load the memory address into register 1 of 100. So now we've done that too, and if we need to, we can also put comments, loads 35 into register 0, and this loads memory address into register 1. And now you can see why it's called load address, because often we use it to load memory addresses into a register. So next, we want to store the 35 at this memory location. And again, that's the store word command. And looking at this store word command, the data that we want to go into memory is located in register T. So that's the first one. So the data that we want to go into memory has to be in the first parameter to the store word. The memory address of where we want it to go goes into the second register. And so notice that's the memory address. And then we just add this offset to the memory address. So the data that we want to store, which is the first parameter, is $0 or in register 0. And see how helpful this is? Now we can just look down here and say, okay, yeah, that's the data I want to put in memory. And the memory address is register 1. Okay, now we have that offset. We need to have 3 parameters. Even though I don't want to use the offset, I want my data to go at memory location 100. I still have to put in a value. So if I don't want to use the offset, put 0 there. So this stores register 1 into memory at location of register 1. So actually it stores the data from register 0 into memory location at register 1. So now let's see this program running in our simulator. We'll go ahead and assemble it. And it was successful and it created the memory.bin file. And I just saved this on my desktop. So let's go ahead and load that into our simulator. Now I've started up the simulator and I've already loaded my loader so that I have the loader instructions right there. Next, I want to select my input file, which is the memory.bin file that I have just created. And now that I've selected that, I need to point my program counter to the beginning of the loader so that my loader can run and load in that new program that I just wrote. And going back up to the start of memory, you can see that I have those instructions in memory. And I'll go ahead and clear the trace and my registers so that we're all back to 0. Now the only thing that I have in memory is my loader at the end and these instructions right here. I just want to show you, we can go 0x100 and view that memory location, and we get all zeros. Now just one little note, if these text fields ever disappear, just make your window bigger so that you can see them again. And just again noting, there is nothing in memory at memory location 0100. Now, going back up here, here's our program, and our PC counter has all zeros in it because I cleared it. And so here's my program that's going to load the numbers into the registers and then store a number into memory. I'm just going to step through this. Now, the first 2 instructions are the first LAD instruction, and remember, it gets split into 2. And you can see that I have this value in register 0. Now it says 23. You can see that up here it says 35, but 23 is 35 in hex. So we loaded a 23 into register 0. We'll go ahead and step through the next 2 instructions. And now we can see that we have 100 in register 1. So here's our memory address. We want to store this at this memory location. So let's go ahead and step one more time. You can see that we're going to store the data that's in register 0 at the memory location that is in register 1 plus nothing. So that, again, that's an offset. So maybe we can do stuff with arrays. And there's other reasons why we would do that too. So let's go ahead and view that memory location, and you can see at memory location 100 that we have the value 23. So 23 got copied from this register and put into memory. Now just reviewing the original program, the first 2 instructions, because a load address gets divided into 2 instructions, puts 35 into register 0. Then the next 2 instructions puts 100 into register 1. And then finally, we take the values stored in register 0, which is 35, and put it into memory at this memory location. Now, when we write assembly programs, we need to keep track of registers and memory ourselves, which is a difference than writing programs in Python or Java because they manage memory for you. So in this case, we need to manage memories. We also might want to write down what we're storing and where we're storing it. Fortunately, the assembler gives you some tools to help you remember what you're putting where, and that's really with this .org. I mean, not only does that tell the assembler to put the next instruction at this memory location, but it also is a sign for you to say, okay, I'm putting my program at this memory location. Now with the assembler, we can also use multiple .org statements in one program. We can use one to say where we want our instructions to go, and then we can use another .org to say where we want our data to go. So now I could put .org, one memory address 100, and that will say, next I want the whatever follows to go at memory address 100. Now we have two more assembly directives, and remember the directives are the ones that start with a period. They don't get translated into ones and zeros like our instructions do. They just tell the assembler how to make things into ones and zeros. So we already know the .org, which tells us where in memory we want to put something, and the .end that marks the end of our program. But we also have a .bss and a .bsc. So again, on our programmer's reference, down here we have our assembler directives. We already know the .org and the .end, and let's go ahead and look at the BSC. And if we read this, it reserves blocks of memory for data storage and initializing the blocks to the values in a comma delimited operand list. So for example, we could do .bsc, and that stores a -2 in a memory location. A .bsc, and this stores 5 at a memory location, and then 10 in the next, and then F in hex, and then a -5. So this stores 4 blocks of words at a certain memory location. So that's what .bsc is it is used to put numbers that are hard-coded into our program into certain memory locations. So where would you use this? Well, oftentimes we have a lot of numbers that are hard-coded into our programs that are just data that we want to use later. And so the .bsc can hard-code those numbers into memory. And I'll show you how to use that next, but let's look at the .bss assembler directive. So the .bss is block storage space, and this reserves a block of memory storage for our data. So we can use the .bss and say, I want to reserve 10 memory spots for our data. And let's go ahead and see how we would use this in a program. So if you notice, I have the .org memory address 100, and then right following it, I have a .bss, and I want to reserve 10 spaces in memory for something. Now, of course, I'm only using one of those spaces, but if I had an array of 10 elements, this would reserve 10 spaces in memory for that array. And then I can have, say, another array of 20 elements, and I can reserve 20 memory spaces that will appear right after these 10 memory spaces. So you don't have to do this, but this is just a good thing to add onto your program because it lets you see where you're putting things in memory. And the best thing about this is we can label these lines. So I can call this array 1, and the second one, array 2. And so now we know that array 1 is going to be located at this memory location, and that array 2 is going to be directly after it. And then when we use our load address, instead of hard coding that memory address, we can use that label that we put right here. So that will say, okay, wherever array 1 is located in memory, and the assembler will figure out, okay, array 1 is going to be located at memory address 100, and it will figure that out. Wherever that is, it will load that address into register 1. So now we don't have to worry so much about where everything is going. I mean, we still have to worry at some, like where our instructions are going to go and where our data is going to go, and we need to make sure they don't overlap. But other than that, I can just label my data areas with these labels. Then I can use a load address to store them up. Now I'm just going to include one here, and maybe I'll just call this my data. And then up here, instead of doing load address 100, I'll just go data. Now this program will work exactly like before, so I can go ahead and assemble it. And notice I saw that it updated and I got a new memory file. And it also says there's 2 segments now instead of 1. That's because it's going to zero out memory for this data for me. So let's go ahead and load this in our TSC simulator. So I still have my loader loaded into memory. I'm going to go ahead and select my input file one more time. And I'm going to load my PC, so it's pointed at my loader, and I'm going to click Start, and now that's going to load my program back into memory. Now, if you notice, memory location 100 got zeroed out. That's because the assembler in the .bin file created, it told the loader to load 10 zeros starting from here on into memory. And then it also loaded my program back in. So I can clear my registers, I'll clear my trace, and I'll step through my program one more time. And still the first instruction is the same. Now the second instruction was the one where I said load address data into register 1. And data was a label, and now I can do that again, and it still loaded 100 in there. So the assembler was able to figure out that my data is going at memory location 100. And then one more time, I will do that store word. And then let's go ahead and view that memory location. Because I did the store word, 23 in hex got copied into memory. So what we can see when I said load address $1 data, the assembler looked to see where data was, and it said, oh, data's at memory location 100, and it linked it up. So that's what's really nice about the assembler with these labels. Not only do they help on branches and jumps to be able to go to different spots, they also help connect up your data location. So if I happen to put something in front of my data, right here. Let's say I decided to do another .bss and reserve 5 memory locations. It would move the data down, but now this would still work even though I moved where data was, because the assembler will link everything together. Now let's go ahead and do some .bsc. So I'm going to call this data2, and I'm going to put some hard-coded numbers in there, .bsc, and we'll just put the number 10 and the number 15 and maybe the number 20 into memory. So let's go ahead and load. So this is the loader that's going to put these numbers into memory. Not my program, but the loader will load these numbers into memory. And so let's go ahead and read one of those numbers out. And again, using my registers, I'll store I'll say this is the location. Right now, we don't know what's in it, but in registers 2, we're going to store data from memory. So we're going to copy data from memory into a register. So after I do this store word, if we want to read something out of memory, first of all, I need to get its memory address. So I'm going to do that maybe in register 3. And I'm going to call data 2. So let's go ahead and down here, register 3. Again, I don't really care what the exact memory is, but this is the memory location of data 2. Okay, so we're going to load the address of this data in a register. And now, instead of storing it from a register into memory, we want it to go from memory into a register. So that's the load word. It does the exact opposite. Now, where do we want this data to go? Again, you can look at the programmer's reference to see this. We want the data to go into register 2. So I'll say register 2. And what memory address do I want to use? Well, the memory address is stored in register 3. And again, we'll use 0 for that offset. I'll show you, the next example will show you if we don't use 0. And this loads data from memory into register 2. So we're using register 3 as the memory address, and we're storing whatever's at memory at that location into register 2. Now let's also put a halt right here, so our program won't keep running on and on forever. Let's go ahead and save and assemble this, and let's load it into our simulator. All right, so let's go ahead and select that input file one more time. So my loader's still in memory. I haven't done anything to memory. I'm reselecting that memory.bin file. I'm pointing my PC counter to the loader, and now I'm going to load in my assembled file by clicking Start. Okay, now if you notice, memory here changed. Why did it change? Well, the .bss that reserved 10 locations for data is right here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, right after the .bss, I had the hard-coded numbers 10, 15, and 20. So here's 10 in hex, 15 in hex, and 20 in hex. So if you notice, it's the loader that read the .bin file and put the .bin file into memory. And the way it did it is it first loaded my instructions into memory, and then it decided to do another segment, and the other segment loaded 10 zeros along with these hard-coded numbers into memory. So the first segment loaded the instructions into memory, and then the next segment down here said put 10 zeros into memory, and then put the numbers 10, 15, and 20. And that's what the BSC does, is it puts hard-coded numbers into there. And that's all starting at memory location 100. So again, at memory location 100 is the 10 zeros, and then the 10, 15, and 20 stored right into memory, along with our program located at memory location 0. So let's go ahead and clear our registers. We'll clear our trace too, and we'll just step through my program one more time. So the first thing loads 35 into register 0. Then the memory address of data with no, just data, not data 2. And it stored 100 in register 1. That's what these two instructions did. So that's the LAD $1 data. And then we'll go ahead and step again. And that's the store word. And we're going to take what's in registers 3 and store it in memory of where register 1 is. So if you notice, register 1 has 100. And if we look at memory location 100, the 23 got copied into memory. So let's take another step. And this is the load address data 2. So if we look at data 2, and notice it put it into register 3. So if we look at register 3, we have 100 in A. So looking at memory location 100 in A is our A. Let's go ahead and step one more time. So now we're going to take the load word. So we're using what's in register 3, which is 100 in A, and we're using that as the memory location. So we get 100 in A. We take the data that's located in that memory location and we put it into register 2. And one more step is our halt instruction, and there our program ran. So notice that this came out of memory and into a register. Okay, well, what if we want to get this 15 or this 20 out? Well, that's where we can use the offset. Let's say we'll load data in one more time, and we'll load it from register 2. So we're just doing the same instruction that we did before, but this time I'll add 1 to my memory address. So this is going to take the number that's in register 3, add 1 to it to form the memory address, and then take what's ever in there and store it in register 2. So let's go ahead and assemble this and load it into our simulator. So I'm just going to clear my trace. I'm going to load in my PC the loader. So I'm going to have the loader load in my program again. I'm going to select my input file, memory.bin one more time. I'm going to run the loader. You could see the loader erased the 23, but it still put these numbers back into memory. So I'm going to clear my trace, clear my registers just in case. And now we'll step through this one more time. So we've already seen this a few times, and we can see that 23 got loaded into memory. Now the memory location 10A or 100A is loaded into register 3. And we can see that the A, notice the load word, we used register 3 as the memory address. So we go up to our memory address, 100A, and it's going to take the data, which is A, and it's going to copy that into register 2. So we'll go one more time. We'll do the next load word. And now you notice it's using register 3 as the memory address. So register 3 has 100A, which is this memory location, but see this 1 right here? So it's going to add 1 to it. It's not going to change it. Notice this still says 100A. It didn't change it, but it added 1 to it temporarily. And so that's 100 in B. And so then it grabbed the data F and stored it into register 2. And then we'll step one more time and halt. So that's how the load word works, and that's how we might use the offset. Now I said the offsets are good for arrays. It's also good for something called a stack. Oftentimes, especially with 4 registers, we'll run out of registers because we need registers to store memory addresses and we need registers to store data. So when we run out, what we usually do is kind of create a stack or have one pointer that points to the beginning of our data. And then if we're going to store 5 different variables, we remember, okay, this variable is stored one offset from our memory address. So it's one position different than our memory address. And that's how we can kind of store lots of data in memory. And then when we want to do some calculations using it, we can use the offset plus our base register and get that data into a register so we can do something with it. So now I'll give you some tips to do program 2 of your lab. You're going to notice you're going to need 2 arrays. So you might want to reserve 50 spots, the lab says, for positive numbers and another 50 spots for negative numbers. So you can go ahead and have 2 arrays be that, and you can call this the positive array and then a negative array. So now you've reserved enough memory to store those 50 numbers that you're going to take in for input. And now you can have those memory addresses. Now, I remember I've always said to use this offset for arrays. The only thing is it's fixed. We can't change this number. So as we store a number into memory, if we want to move to the next number and we're doing this inside of a loop, we can't change this offset each time through the loop. So what can we change is the pointer. So my recommendation is start off with the pointers pointing to your array, and then as you add numbers into the array, move the pointer and keep the offset at 0 because you can't change the offset from loop to loop as you go through and do each loop. You'll have to change where the pointer points to instead. So hopefully this will give you enough to be able to complete the second program, and you're going to want to store words into memory. Now, one other hint, if in that program 2 that you're going to do, you want to read in numbers from the I/O console. But remember, the loader is going to make you take your input source from a file. So you're going to read your program using the loader. You're going to read a program from a file into memory. Next, you want to run your program, but now you want the input to come from this I/O console. So don't forget to shut off the file input by clicking on console. That way, when your program asks for data, it doesn't try to read it out of a file, it'll read it out of a console. So once again, the steps will be to load your program in. You'll select your input file and you'll load your program in by pointing it to FFF5 and clicking Start. After your program's in memory, make sure you click on Console so that you're reading the data from the console and not your program file anymore. And that way you can enter positive and negative numbers as you run your program.